Ben's given me a very flattering introduction. Really what I do is actually far more simple than he made out. I just look at ice sheets and I try and understand how they work. I'm interested in kind of the big picture, how ice sheets and climate interact and how they can control sea level over time periods ranging from you know, thousands, tens of thousands of years right up to actually just a few decades, or you know, talking about future projections, maybe a century or two. So lots of diverse interests there. What I'm going to sort of present today, we're going to sort of start out with some paleoclimates, then we're going to very quickly jump into some future projections, and then we're going to come back to paleoclimate via a different route to sort of ask a few questions as to whether what we're doing is the best way to go about solving the problem. So yeah, next slide, please. Excellent. So hopefully this kind of plot is at least familiar to a lot of you. I know there's a wide range of backgrounds in this audience, but basically what we're looking at here is the way that Antarctic temperature changes over the last, in this case, 500,000 years, and how that relates to changes in CO2 in that top panel, but also looking at how that change relates to changes in global sea level, in this case from a relative sea level proxy. And you can see that pretty much, apart from a few sort of leads and lags, these are pretty well matched. So we can basically say that these are very tightly coupled systems, and that changes in one component, in temperature or CO2, relates to the others, and the ice sheet volume and sea level change in coincidence with those forcings. Next slide. Now, as we go to the longer time periods, that relationship is kind of harder to define because our proxies are less certain. That top panel there is showing you CO2 changes over the last 430 million years, so a very different time scale. And there's some uncertainties, of course, on those proxies, but an interesting pattern, and one we'll come back to later. The same data is shown in that lower panel, but it's on a kind of strange plot. Basically, the y-axis is a log scale, and the x-axis is sort of chunked up into different bits. So we're going from hundreds of million years in A through to a few million years in B, and then getting to shorter time frames. But the reason for showing this is to show how CO2 variations in the past sorry, is there...
So you're right.
Sorry, I can just hear some background noise. Just to show the context of where we're headed in terms of the future scenarios, those RCP scenarios for the next few centuries in the context of the longer term CO2 changes. Next slide, please. Okay, so on the bottom here, we're seeing that basically the same curve, but this time showing it in terms of paleo temperature rather than CO2. And the reason for showing this here is to put the present changes in context. In that top left panel, you can see historical CO2 emissions, in this case, just the last 15 years, from 2005 through to 2020. And this paper was basically showing that over the last 15 years, our CO2 emissions have been tracking the RCP 8.5 scenario. So basically following that worst case scenario, which is pretty alarming. And the top right figure there shows that the ice sheet response in terms of the sea level contribution has been also tracking that worst case scenario as well. So things are not really going according to plan. We don't want to be following this trajectory, because as the bottom chart shows you, if we follow that RCP 8.5, so on the far right hand side, that sort of orangey red color, that's going to take us into a climate space that we haven't seen for probably the last at least 3 million years, and probably, you know, if things get really bad, we could be getting back into the Miocene, you know, sort of 15, 20 million years ago, or worst case, get back into the Eocene. And when you talk to geologists about the Eocene, I mean, this is a crazy kind of climate. We had, you know, sort of crocodiles at the poles. it was a very, very different world. And it's certainly one that we don't really want to go to, because I don't know how humans would survive that kind of world. So alarm bells really in that respect. Okay, next slide. Now, this is one of the nicest figures I think I've seen that shows the RCP scenarios and future pathways. I think it's a very intuitive way to understand kind of where we are in this space. This is from Malte Meinshausen and his group. And basically, we're looking at the sort of the temperature change through the historical period up to that sort of present day gateway, if you like, and then the future projections showing this sort of diverging set of pathways. And shown here are not just the RCP forcings, the emissions forcings, but also the socioeconomic pathways. So basically thinking about the ways that society manages themselves and sort of global relationships over the coming centuries. So basically the point here is that we have choices and we can decide which of these pathways we follow. Next slide, please. Now, the reason that it's important we make these decisions consciously is because if we don't, we run the risk of heading into a very uncomfortable world, as I just alluded to. This figure is from a paper from Will Stephan and others a couple of years ago, and it got a lot of media at the time, and it's a really interesting paper. Basically, it was a thought piece that they put out saying, you know, what happens if these worst case things kind of play out? And what they're saying here is that under a natural system, the sort of glacial interglacial cycles that I showed at the beginning are kind of what's governed our climate for the last at least 500,000, maybe million years. And the Earth has kind of sort of rocked backwards and forwards in this, what they call this limit cycle of glacial interglacial climate variability. Now, we've already done enough to the climate that we've prevented us going back into another glacial cycle. And what they're arguing in this paper is that with some serious stewardship, we can just about bring our Earth back to what they say here, you know, stabilized Earth. It'll be kind of warmer than it was before, but, you know, we can deal with it and things will be okay. The danger really is that if we don't get on top of things, we pass this planetary threshold, lots of feedbacks kick in, and we have this runaway into this sort of hothouse Earth environment, and that's obviously a big concern. Next slide, please. How do we get there, and what does this mean for the ice sheets? Well, one of the things that's kind of come out of the last decade or so of ice sheet research is that actually ice sheets are remarkably sensitive to even small parts, small changes in temperature. You know, we used to think ice sheets were pretty inert, immobile, they were slowly responding to climate changes, but actually they can respond pretty quickly, and they can respond in a large magnitude sense over a long period of time as well. So when we look at the evidence from model experiments, from paleo data, we can see that actually just a couple of degrees of warming, something like the Paris Agreement, 1.5, 2 degrees, is enough to destabilize these ice sheets in Greenland and Antarctica. And so the big question then becomes, you know, not so much how much the ice sheets are going to contribute to sea level, but the rate at which they're going to do that. That becomes the real question. Next slide, please. Now, of course, paleo can give us an insight into this, at least in one respect. When we look back at the last time that global mean temperatures were sort of 1 or 2 degrees above present, that was about 125,000 years ago, the last interglaciation. And the world was quite different then. Sea levels were 6 to 9 meters higher than present. We think we lost quite a large chunk of West Antarctica. We lost part of the Greenland ice sheet. Glaciers around the world melted. The ocean expanded because of the heat. It was a very different world. How quickly we got there is still open for debate, but in the simulations that we've done, we can show that at least the Antarctic ice sheet was probably contributing 20 or 30 centimeters per century to that overall sea level rise. So by the time you couple in the other components, it's certainly similar to what we're projecting for this century. Next slide, please. So how do we make projections? If we go back less than a decade to what was done in the last assessment report for the IPCC, the state of the art really in terms of the modeling was pretty crude in that essentially we were quite good at doing mass balance calculations. So calculating how much snow was going to accumulate on the ice sheet, how much was going to melt under a warming climate. The thing that we weren't very good at then was calculating the dynamic contribution of these ice sheets. So how much internal mechanisms were going to play a part in mass loss. So when it came to assigning a dynamic component to the projections, these were essentially estimated, and nobody really knew whether those estimates were scenario dependent or not. So this triggered a big community effort. Next slide, please. So over the subsequent few years and leading up to the special report on oceans and cryosphere and changing climate that came out last year, the ice sheet community put a lot of time and effort into building new models and trying to incorporate mechanisms that would realistically capture these dynamic responses, so the internal changes to the way an ice sheet flows. And a lot of these relate to instability mechanisms, so things where a system is destabilized and then can continue changing even in the absence of an applied environmental forcing. But even by 2019, the number of scenario-based simulations that were using these more advanced models was relatively small. And so the projections changed a little bit, but not a great deal. Next slide, please. Since then, there's been even more concerted effort to formalize the way we do projections, and going into AR6 now, we now have a suite of simulations from 14 different modeling groups around the world using models of different complexity, but using standardized experiments. And the idea here is that we can see where the commonalities are, see how the models agree. And for Greenland, actually they're pretty consistent. So lots of different models, but they're all showing a good sort of scenario dependence in terms of the projections. You can see there how the scenarios are diverging quite nicely. And that's because in Greenland, we're looking mainly at a mass balance effect. Essentially, it's all down to how much the air warms and how much melts at the surface. In Antarctica, next slide, please. It's quite different. So here we've got a big uncertainty due to the dynamic response of the ice sheet, not so much the sort of surface melting. And you can see there that there's a huge spread amongst the forced models. Lots of uncertainty. We don't even know whether the ice sheet's going to grow or shrink, which is a pretty big uncertainty. And it's one that AR5 struggled with. We're still struggling with it despite these much more advanced models. And this is something that we're working hard on at the moment, trying to really understand what these numbers are telling us. Next slide, please. I'm very glad Ben mentioned this paper that he had out earlier this year, because this is a slide from that paper, and it's actually a really, really nice way of showing the consequences of these uncertainties in the projections. And I'll just quickly sort of draw your eye down to that bottom right figure, the RCP 8.5 over the period to 2300. And you can see, if you look at the x-axis, the numbers there are very, very different to the other panels. The key thing here is this is all about the ice sheet response. I hope I'm not getting this wrong, Ben. But essentially what we're seeing here is this is expert elicitation. This is experts' best guess as to what the sea level might do over the next century or two. And we just really don't know because of that uncertainty, the deep uncertainty that exists in the way that the Antarctic ice sheet is going to respond. So for policymakers, this is a real issue. And it's something that we're really struggling with in terms of how we communicate this uncertainty in a useful way to people that kind of need to know this information. Okay, next slide, please. Now, of course, that sounds pretty bad, but actually there are things that we do know quite well. And we do know that, for example, when we take an ice shelf away, the ice sheet is going to respond quite dramatically. And we've done sort of more conceptual experiments, again using a range of models, where we take away the ice shelves, the floating ice that holds back the grounded ice that contributes to sea level. And when we take that away, we see a dynamic response from the ice sheet, which is captured pretty much by all models. So that's kind of reassuring. We do know that we're capturing the right kind of responses. What we're seeing in terms of the model output is a difference in the magnitude of that response. And so that's an area that we need to work on. Next slide, please. But the take-home message in terms of policy really is that because of these dynamic feedbacks, mitigation doesn't equal stabilization. And this is something that we try and hammer home to anyone that will listen, really, because we can stop emitting right now, but actually the changes that are going to ensue will carry on for the next several hundred years and probably thousands of years. So really what we need to do as a society is understand that there is already some committed response, but fully buy into the fact that we have to mitigate as much as possible, because this not only slows down the process, but it limits the eventual outcome. So it kind of buys us time, and it limits the damage. So that's the message that we try and get across from an ice sheet perspective. Next slide, please. Okay, so this is where we start going back again into the paleo and start thinking, well, is what we're seeing now and projecting for the future similar to things that we've seen in the past? You know, I showed you that slide before of the last interglaciation where we lost you know, a large chunk of West Antarctica. Now, when we look at the last sort of 500,000 years, actually the interglacials have actually all been very similar, except for our current one. Hopefully you can see the panel on the right-hand side there, which shows that our current interglacial is really anomalous. When we go back to interglacials even earlier in the Pleistocene, we see similar kind of mass loss to the last interglacial, 6, maybe 13 meters of sea level equivalent. And this is not always because the climate was a lot hotter. Sometimes it was just because it was a little bit warmer, but for much longer. So we end up with this insight from the paleo in that we can basically get to the same state in a number of different ways. And of course, the paleo tends to tell us more about the end game than it does about the rate. So we have this problem of sort of equifinality, and how do we understand that? How do we understand the rate of change of a system? Next slide, please. When we think about these systems, we tend to think of them as complex systems that are controlled by feedbacks. And this is a sort of get out, really, because we can only do so much with process-based models. We can put various things in there, and anything that isn't in there can be used as an excuse for not getting the right answer. And of course, you know, we can't have models that include everything. It's just not possible. But we do know that feedbacks are essential, and actually we can't reproduce the patterns that we see if we only have single forcings. So we're left in this position where we know we have to include multiple forcings. We know that the sum total is more important than the individual, but we don't actually have an adequate way of robustly simulating those in an explicit physics-based way. Next slide, please. So one approach that I'm sort of exploring at the moment in order to sort of understand climate over sort of glacial, interglacial cycles is to think about it more holistically and say, well, what if we can understand the system response as a whole, even if we don't understand all the components? And here's an interesting thing. There's approaches in dynamical systems which look at just the way systems behave under different forcings. And here we've got a very simple equation which has been known about for many years, and it's one of a family of equations like the Lorentz equations, where basically depending on an initial state, you can get very different outcomes. And what we're showing here is just how this one equation predicts evolution of a system that depends on that initial condition of the value of the lambda term in that equation. Now, nothing else is changing. We're just evolving that equation through time, depending on different values of lambda. And you can see that it goes through a range of different states. We go from a nice stable state to one that's kind of nicely oscillating, to one that's kind of oscillating a bit more freely, and there's period doubling happening there. And then you get to a point in the red where it becomes essentially chaotic, and eventually the system breaks down. And this kind of system it's a complex system. It behaves in a way that many complex systems behave, in that it exhibits bifurcations, and you have these sort of different states. But the key thing here is that when we allow lambda to evolve as a time-dependent variable rather than just an unchanging initial condition, you can basically go from one state to another, not in a linear way, but in a very non-linear way that eventually ends up giving you this kind of sigmoid in the red line in the bottom right there, that ultimately ends in a state of collapse. So this is basically a critical system. It reaches a state of critical instability and then collapses. Next slide, please. Now, if you take that red line in your head and flip it upside down and then allow the system to recover, you can end up with what we see there at the top left. You see this kind of sigmoid again, one that starts high, drops, kind of flatlines towards the bottom, and then abruptly jumps back up. And we can do things like add white noise, we can add noise, we can smooth it, we can do all sorts of things. And you can see that essentially the shape of that curve is very similar to what we're seeing in that record, that proxy record at the bottom left there, which is essentially from an Antarctic ice core for the last 400,000 years, telling you about essentially global temperature through time. We can see the same peak, we can see the rapid drop, the gradual approach to a minimum, and then this sort of rapid rebound. So I think there's an argument here to say that actually these late Pleistocene glacial cycles behave as this kind of critical system. Now, what's really interesting is if you look at the panels on the right-hand side, the middle panel there is that Antarctic ice core record. Again, a slightly different version of the grey line is the modeled relationship. On the bottom is that CO2 relationship that I showed you right at the beginning, that's covering 400 million years, so a very different time scale. And the top panel is showing you in the blue line the response of the sinoatrial node of a mouse heart. So we're looking here at the membrane potential across cells, non-myocyte cells in a mouse heart. And this is, these cycles are operating over milliseconds. So we've got lots of different timescales here. And of course, there's no causal relationship between these, but the point is that with a simple model of a dynamical system that approaches a state of criticality, you can simulate essentially the behavior of three very, very different systems. Next slide, please. Okay, so the interesting thing about critical systems is that they've been known about a long time, and you can simulate them very simply. And the canonical example of this is the so-called sand pile model that Per Bak and others came up with a few decades ago. And essentially what we're doing here is just growing a numerical sand pile. We're adding a sand grain one at a time, seeing how that pile of sand grows. And of course, as it grows, it starts to collapse, and each collapse maybe triggers other collapses and so on. And so we do this in a numerical sense, and you can see how this system evolves. Next slide, please. Now, what's interesting is if you look at the mean pile height, so basically the average height of the grains in that artificial domain, and you map that out over 10,000 iterations, in those top panels, you can see we start out with nicely symmetric cycles as the average height of the domain sort of rises and falls. But as it becomes more developed, the rise and fall becomes increasingly asymmetric. It starts looking very much like those climate cycles. Now, what I didn't show you earlier, but people discuss a lot in the Palaeo-Pleistocene world, is this transition from 40,000 year glacial cyclicity, which is very symmetric, to 100,000 year glacial cyclicity, which is very asymmetric. Now here we can reproduce that transition simply as a dynamical consequence of system evolution. There's no change in the forcing. All we're doing at every time step is just adding one more numerical sand grain. So there's some interesting insights that we can get there into how the climate system might be behaving without necessarily having to invoke a lot of extra sort of environmental processes or feedbacks. Now the middle panel there is showing you, in the vertical bars, is showing you the number of collapse events within that, that sand pile. And when we look at the frequency plot of those on the bottom there, you can see that the high frequencies, sort of near the top, they essentially drop out, and the collapse events are happening at much more lower frequencies. So essentially the collapse events are, they're less frequent, they're much bigger, and the build-up is more gradual, followed by a much more abrupt collapse. Next slide, please. So essentially the system is beginning to synchronize. More and more parts of the system are behaving in sync with each other. And to think about that, we need to go back to, again, canonical examples of how synchronization evolves in systems, in dynamical systems. And the work that was done the end of the last century, 1998, a real seminal paper by Stephen Strogatz and others, basically looking at modeling synchronization with network theory. So taking, in this case, a ring lattice network and saying, let's see how these systems behave under different conditions. And on the top left-hand side there, you can see a regular lattice where each node of that network is just connected to its nearest couple of neighbors. And you can imagine that trying to get a message from one side of that lattice to the other is quite slow. It's pretty inefficient because it's got to go through all the intervening nodes. On the sort of furthest right of those three panels, the random network, this is where nodes might be connected directly to their neighbor. They might be connected to the other side of the network. It's a real mess. But that's much more efficient in terms of actually getting a message from one part of the domain to another. Now, the interesting thing about this is that actually you don't really need to have that fully connected system. What you need is just to have a few sort of global connections in order to get the benefits of the most of the efficiency gains of that bigger connectivity. So the lower panels basically show my implementation of that sort of network connectivity thing, just to show you this sort of step change that occurs. Essentially the rewiring that takes place on the x-axis is just moving those connections, and the average path length on the y-axis, it gets smaller as you go up. That's basically a measure of efficiency. So you can see that as the rewiring proceeds, as we move towards the right of that graph in the bottom right, there's a phase transition, essentially a step change, where you see a rapid increase in the efficiency of the network, and then you get to a certain point where actually any more rewiring doesn't really give you a much more of an increase in efficiency. Next slide, please. Now this is kind of interesting because we can actually see that in other network theory examples. It's not just about rewiring. Sometimes it can be about just adding connectivity to existing nodes. So the top left example there is another paper showing exactly the same sort of thing. And you'll start seeing that there's this sigmoidal function there, which is very similar to that one I showed you earlier, that red line in the bottom left. And just to hopefully convince you even more, when we overlay these two data sets, we can see that it's tracing out the exact same curve. Now, of course, there's no causal link here. One is in state space, the other, my stuff, is in time domain. But I think by looking at these two things together, we can start saying, well, what's happening during this period of rapid change in the glacial interglacial cycle? And my idea here is that essentially this rapid change is the glacial inception. This is when the climate system is essentially doing some rewiring. It's building connections that are global, not local, And it's essentially building this framework for synchronization. It's allowing different parts of the system to talk to each other and transmit information at short time periods. Okay, next slide, please. So wrapping things up here, essentially, what I'm trying to get at with this understanding of climate in the broadest sense is that if we can model these sort of late Pleistocene climate cycles as critical systems, then we can actually learn a lot from these other approaches that tell us something about those systems. And from this approach, we could say that the interglacial period is actually the period of greatest stability, not instability. And things during those periods, the system is locally coupled. We've got feedbacks that are self-regulating. They tend to keep themselves in check. When we go through that rapid cooling phase, as I mentioned, that's when I see this greatest potential for the system to build connectivity, and positive feedbacks during this time are the things that are dominating the system response. And we can see in the earlier graphs that basically the rate of change during that time is greater than the forcing. So there's things that are amplifying the applied forcing. Once you've got to a point of maximized connectivity, the climate goes into this waiting time state. And this is kind of an interesting thing we can learn from that heart model. Basically, the sinoatrial nodes all kind of get to a point where there's tens of thousands of them that accumulate charge during this sort of build-up period. But the heart only beats once all of them have got to the point where they're ready to fire. If any one of them kind of fires and the others aren't ready, it doesn't matter, it doesn't make any difference. They all need to be close to that state. And that's why waiting time is really important. So again, the analogy here is the climate gets to a point where different parts of the climate system all need to be approaching this state of criticality. Once they're there, then they're in a state of where they can be synchronized, and any one component of the Earth system can then be the trigger that propagates through the whole network and triggers a glacial termination. And so my analogy here is that this is a system of Jenga, not dominoes. This is pretty deep stuff, I know. But when we think about, people talk about sort of the domino effect and so on, but actually dominoes, when you think about them, are very predictable. They tend to fall in a nice, neat, linear way. And actually, if you took one of them out halfway through the system, then the collapse would just stop. And there's nothing chaotic about it at all. Whereas in Jenga, we see a much more globally coupled system in which if you take any one block out, if it's the critical point, then the whole lot will collapse. And there's no real way of knowing which way it's going to go or which block is going to be the key point. So the take home from all this, I know it's a little bit abstract, but I guess what I'm getting at is that we often, both in paleoclimate and in future projections, we get so hung up on thinking about an individual forcing that we lose sight of maybe other things that are more important. And I think what I'm getting at here is that if we can do more to understand connectivity between Earth system components and the way that they may or may not be synchronized, then I think we can learn a lot about what may happen in the future. Okay, last slide then, please. Okay, so I started out talking about ice sheets and then went off on a pretty big tangent, I know that, but hopefully I've shown you that there are some interesting things we can learn there. And I think one of the things that we now know that we didn't maybe a decade or so ago is that the ice sheets are very sensitive to small changes. This becomes important when we think about other parts of the system that are maybe getting close to tipping points, and we're likely to see this sort of cascade going through the system. So I'll leave it there, and I hope that the technical problems at the beginning didn't put you off. I hope there's been something of interest to at least some of you there, and of course I'll take questions if there are time for questions. Thank you for listening.